Okay, for this question, the set of all convergent sequence of real numbers uh, is a vector space. Okay, is a vector space over a field of real numbers. Okay, or a field of real numbers. So your claim is you want to show that it is the vector space. So you want to check there are 10 axioms. If 10 axioms are satisfying, then we can say that this convergent sequence of real numbers form a vector space. Okay. So for this question, let as usual addition and multiplication like a coordinate wise. Okay, here also we can use it at parts, right? There is no specific addition and scalar, there is no specific addition here, right? Only the usual addition. You know, take alpha is a sequence, alpha 1, alpha 2, these are the sequence, alpha 3, and so on, alpha n. Nth sequence is alpha n, okay, and so on. These are the sequences, okay. These are the sequences. We can notify this one is alpha. Another sequence beta. This is beta 1, one of the sequence, beta 2, another sequence, beta 3, another sequence, and so on. Beta n, another sequence, and so on. Next is gamma, another sequence, gamma 1, gamma 2, gamma 3, and so on, gamma n, and so on. It is these three are sequences. Okay. Sequence and also convergent, right? Convergence. B a convergent sequence of convergent sequence of real numbers. Convergent sequence of real numbers. Okay. Convergent sequence of real numbers. So check the first axiom. First axiom is a closure property, right? Closure property. So you take two, you can add these two sequences, alpha plus beta. Suppose here is alpha is a set of all, the set of all sequence. We take one of the sequence alpha, and a sequence beta, in a sequence gamma. Okay. First property is closed under the addition. Closed under addition, that means this alpha plus beta also one of the convergence sequence. Your claim is you want to show that alpha plus beta also one of the convergent sequence. Okay. I think you somewhere else you studied, right? I think is the limit process parts we studied. Suppose two sequences are convergence, then addition, that means Sn and Yn two sequence, that one convergence, then Sn plus Yn also convergence, Sn into Yn also convergence. That result we will use here. Okay, right. Suppose alpha plus beta is alpha 1, alpha 2, and so on, alpha n, and so on, beta 1, beta 2, beta 3, and so on, beta n, and so on. Right? Suppose alpha 1, here I already mentioned here, we can use the usual addition for a coordinate wise. Here suppose alpha 1 is one of the convergent sequence, beta 1 is one of the convergent sequence, then you can add alpha 1 plus beta 1 also convergent sequence. That means here alpha 1 plus beta 1, this one also convergent sequence. Similarly for alpha 2 plus beta 2 is also convergent sequence, and so on. Alpha n plus beta n also convergent sequence, and so on. Here each of these values are convergent. Therefore, alpha plus beta is convergence. Alpha plus beta is convergence mean it is one of the element of this convergent sequence set. Okay, one of the element of convergent sequence set. Therefore, closure properties satisfy. Okay. Is, then we will write is also, this one is also convergent. Therefore, this means is closed under addition. Under addition. Next, we want to check the axiom number 2 is commutative. Suppose alpha plus beta, claim is alpha plus beta equal beta plus alpha. Okay, right. Let's to take alpha plus beta. Alpha plus beta means alpha 1, alpha 2, these are the sequences, alpha n and so on, plus beta 1, beta 2, beta n and so on. These are the sequences. Okay, these are the sequences. Okay, beta n. So suppose, right, I already told you we can add coordinate wise. Okay, this usual addition, alpha 1 plus beta 1, alpha 2 plus beta 2 and so on, alpha n plus beta n and so on. You know, we will write alpha 1 plus beta 1. Alpha 1, one of the sequence in the real numbers. Beta 1, one of the sequence in real number. If you change the orders, doesn't matter. Okay, you can write here like this. It's beta 1 plus alpha 1. Suppose alpha 1 is one of the convergent sequence and beta 1 is one of the convergent sequence. Then alpha 1 plus beta is convergent sequence. Beta 1 plus alpha 1 also convergent sequence. That's why this one also convergent sequence. This one also convergent sequence and so on. Again, the orders, right? So, because set of this convergent sequence of real numbers now, convergent sequence of real numbers, therefore, it is should satisfying the commutative law, right? It should satisfying the commutative law. Therefore, we can write like this, okay? Right. So this is your beta 1, beta 2, and beta n is n sequence and so on. Here alpha 1, alpha 2, alpha 3, alpha n and so on, right? It is your beta, it is your alpha. Thus, this addition is commutative, right? Thus, this addition is commutative. Okay, thus this addition is commutative. Next, we want to check the associative property. That's why we define the three terms, alpha, beta, and gamma. Okay. Next, we prove the associative property. So, for next one, you already know what is the value of alpha and beta and gamma. Okay. Now you write alpha is alpha 1, alpha 2. There are convergent sequences. Okay. Alpha n and so on. Here, otherwise you can put like this mark. You know, beta is, what is the form? Beta plus gamma. Here, alpha plus beta of the form this one. Similarly, beta plus gamma, beta 1 and gamma 1, no? Then we will write easily beta 1 plus gamma 1, gamma beta 2 plus gamma 2. There's no need to put bracket. Okay, right. And beta 3 plus gamma 3 and so on. Beta n plus gamma n and so on. Already know that? Okay, right. Now, it is one of the sequence. You take this one of the sequence, is another sequence. Then again, you will add. Then you get alpha 1 plus beta 1 plus gamma 1. Alpha 2 plus beta 2 plus gamma 2. Alpha 3 plus beta 3 plus gamma 3. And so on. Alpha n plus beta n plus gamma n. Like a previous commutative law, I already mentioned here. The commutative law I already mentioned here. It is we will write alpha 1 plus beta 1 equal to beta 1 plus alpha 1. Like this here also. Here each of the sequences, alpha 1 one of the sequence, beta 1 another sequence, gamma 1 another sequence. These are the real numbers. Okay, real numbers of sequence. Therefore, the real numbers should satisfy the associative property. Then you will write alpha 1 plus beta 1 plus gamma 1. Alpha 2 plus beta 2 plus gamma 2. Alpha 3 plus beta 3 plus gamma 3 and so on. Alpha n, beta n, gamma n and so on. Okay. Now this one we will write alpha 1 plus beta 1, alpha 2 plus beta 2 and so on, alpha n plus beta n and so on, plus gamma 1, gamma 2, gamma n and so on. Is it okay? Gamma n and so on. This one we can write alpha 1, alpha 2 and so on, alpha n and so on, right? Alpha n and so on, plus beta 1, beta 2 and beta n and so on, plus gamma 1, gamma 2, gamma n and so on. So this is your alpha plus beta. It is your gamma. Therefore, set of all convergent sequence satisfy the associative property. Okay, set of all convergent sequence satisfy the associative property. Thus, addition is associative. Addition is associative. Next, for identity values, for identity sequence, set of all identity sequence of the form like this, right? You take alpha plus this sequence. This is sequence of the form. The sequence of the form. It is sequence of the form alpha 1 is 0, like that. You know, what is the form of this sequence? 0, 0, 0, 0, 0, and so on. Okay. So, you add these two, then you again get alpha 1 plus 0, alpha 2 plus 0, alpha 3 plus 0, and so on. It is your alpha, again alpha 1, because in the real number, alpha 1 is one of the real number, plus 0 is a identity in real number. Then again you get alpha 1, alpha 2, alpha n, and so on. It is your alpha again. Thus, your identity is this one, right? Thus your identity is this one, 0, 0, 0, and so on, 0, and so on, is an additive, right? Additive identity. Okay, it's additive identity. Next, you want to find the inverse, right? Next, you want to find the inverse. Inverse is let your alpha is sequence alpha 1, alpha 2, and so on, alpha n, and so on. Okay, then what about the inverse sequence? What is the minus alpha is defined by each of the terms should be said. You want to multiply each term by minus 1, then minus alpha 1, minus alpha 2, and so on, minus alpha n, and so on. What about this alpha plus minus alpha? Okay, alpha plus minus alpha, it is equal, okay, alpha 1, alpha 2, alpha n plus minus alpha 1 minus alpha 2, and so on, minus alpha n, and so on. You know, it is the element that inverse is this one. You add this 2, you can get the identity, because it is identity, because alpha 1 at this one you get this value, alpha 2 plus minus alpha 2, then minus, sorry, alpha n plus minus alpha n, and so on. So it is 0, 0, 0. It is your additive identity, no? Then this is your additive inverse. Thus this one is your additive inverse. Okay, thus it's minus alpha, no? Minus alpha is minus alpha 1 minus alpha 2, and so on, minus alpha n, and so on, is an additive identity. Okay, additive identity. Next, check the closure property for the scalar multiplication. You know, in the, I again repeat it, in the uh, conveyance sequence, one of the properties, suppose E is one of the scalar, Sn is one of the sequence, then you check the limit. Suppose Sn is convergence, then Cxn also convergent. Okay, Sn is convergence, then Csn. So multiple of the scalar one. C is one of the scalar one. Then Cxn also convergent. This property we will use again for the next part for a closure property. Action number 6, let C belong to real. Then C alpha, it is, you don't know that C alpha 1, C alpha 2, C alpha n, and so on. As usual, scalar multiplication. Inside you can multiply each of the values. Okay, you know, alpha 1 is convergent, therefore C alpha 1 is convergent. Alpha 2 is convergent, C alpha 1 is convergent, therefore this one is convergent. Okay, therefore it is also convergence, because each of them convergent, therefore it is also convergent, means C alpha is convergence. C alpha is convergence, it is one of the element in this set. It is also convergent, therefore it is one of the element in this set, therefore it is closure, right? It is closed under scalar multiplication. This closed integral multiplication. Next, action number 7. You take let C belong to real number and to take two vectors C times alpha plus beta. This one is C times alpha is alpha 1, alpha 2, alpha 3 and so on alpha n plus beta 1, beta 2, beta 3, beta n and so on. Next, you add this use addition alpha 1 plus beta 1, alpha 2 plus beta 2, alpha 3 plus beta 3 and so on, alpha n plus beta n and so on. So this one is your C times alpha 1 plus beta 1, C times alpha 2 plus beta 2, C times alpha 3 plus beta 3, okay, C times alpha n plus, C times alpha n plus beta n and so on. Here each of the elements are alpha 1 plus beta 1 also the real numbers. C is one of the real number. Then you can use a distributive law here. So use the distributive law here. Then you will write here C alpha 1, C beta 1, C alpha 2, C beta 2, C alpha 3, C beta 3 and so on. C alpha n, C beta n and so on. Okay, C alpha n, C beta n and so on. This one we will write of the form this one. C alpha 1, C alpha 2 and so on, C alpha n and so on, plus C beta 1, C beta 2, C beta 3, C beta n and so on. Suppose you take this C's, then this is on alpha 1, alpha 2, alpha n and so on, C beta 1, beta 2, beta 3, beta n and so on. It is your C alpha, it is your C beta. Okay, it is your C alpha, it is your C beta. It is action number 7. Next, we will check the action number. Next, we will check the action number 8. Okay, action number 8. Action number 8 is take two scalar. Let C comma D belong to real and one vector alpha. No? Alpha. So you take this one C plus D alpha. It is C plus D alpha 1, C plus D alpha 2 and so on, C plus D alpha n and so on. Here also you can use the associative property distributive law here inside, then C alpha 1, D alpha 1, C alpha 2, D alpha 2 and so on, C alpha n, D alpha n and so on. Then you will write this one C alpha 1, okay, C alpha 1, C alpha 2 and so on, C alpha n and so on, plus D alpha 1, D alpha 2, comma, D alpha 3 and so on, D alpha n and so on. So this is here this is your C into alpha 1, alpha 2, alpha n and so on. D into alpha 1, alpha 2 and alpha n and so on. So this is your C alpha plus D alpha. Right. We'll write here. It is your C alpha plus D alpha. Okay. C alpha plus D alpha. Now check the action number 9. Now we'll check the action number 9. Okay. Now we will check the action number 9. Now we will check the action number 9. Okay. Check the action number 9. Let C comma D belong to real numbers. Alpha equal alpha 1, alpha 2 and so on. Therefore, CD into alpha. CD alpha 1, CD alpha 2, CD alpha n, right? CD alpha n, CD alpha n and so on. CD alpha n and so on. Then we will take this one, right? Then for this part, C times, for this one, C times, then this is C alpha n. Then what is this? We will write this one as C into D alpha 1, D alpha 2, D alpha n and so on. So this is C D alpha, C D alpha. Okay, it is action number 10. Okay, now you vary the action number 10. Now you verify the action number 10. It is 1 into alpha. It is 1 into alpha is unit value 1. So 1 into alpha is, you will write 1 into alpha 1, 1 into alpha 2 and so on, 1 into alpha n. and so on. So this is alpha 1, alpha 2, alpha n, and so on. It is your alpha, right? It is your alpha. Thus, all 10 axioms are satisfying. Then we can say that, okay, thus all 10 axioms are satisfying. Then we can say that set of all convergent sequence form a vector space. Okay, the set of all convergent sequence form a vector space over the over field of real numbers, over field of real numbers, over field of real numbers. Okay, over field of real numbers. Okay. Okay, next question. B is the set of functions from real number to the positive real numbers. The positive real numbers. That is, V is the set of function. V is the set of function F with domain R such that f of x positive for all x belong to real number. F of x positive, strictly positive for x belong to real number. Let f g in V, let f and g in V we define vector addition and scalar multiplication by defining the values this function take at any x belong to real number. Okay, by defining the values this function take on at any x belong to real number. Function take on at any real number. So this is defined by like this. This is C here. So that V is a vector space. V is a vector space. Okay. V is the vector space. First one, closure property, let f comma g in V. Therefore, this f of x and g of x should be greater than 0. Now you take the addition, vector addition, it is fx gx. Both are positive, there this one also positive. This one is positive means this one is positive. This one is positive means this f breaks up. Sorry, not it is a vector addition. So it is vector addition g, f and g. This one belongs to V. Thus closed under addition. Right? Thus closed under addition. Thus close under addition. Next one, right? Thus close under addition. Next one is commutative. Let f comma g in V, then f of x and g of x both are positive for all x belong to real number. Okay, for all x belong to real number. So its addition, this one is, we will write this one is fg. Here important, now is important. Is it okay? In general, it's not true. For this case, here V is a set of functions f with domain real number such that f is positive, okay, x belongs to real number. Here we define f plus g and c plus f defining the values, this function. Right? This value is not this values is not depend on x values. Okay, this value is depend on the numbers, real numbers. So in the real number you can use the associative part, sorry, commutative part. Okay, then you can write it. Understand? Suppose if take this function, generally fg not equal gf. Okay, here for the particular case, okay, here you get the defining like this. This is a vector addition and scalar multiplication defining the values this function take, and at any x belong to real number, right? At any x belong to real number, then you take particular point. That point is not dependent on x values. Okay, that is a point. That means x belong to real number values. Then we will write fg equal gf. But gf means g is a direct sum, sorry, g this vector addition of f. This means addition is commutative, right? Thus addition is commutative. Thus addition is commutative. Okay, thus addition is commutative. Next, we want to check the associative part. For associative, you want to take the three functions. Let h in V for all x belong to real number. So this is right. It is we define like this. F x. This one equal. How we can define this one? F of x. Sorry. So this is defined like this, no? So like some. This is okay. Right. Next, you already know that in the right. You already know that this function also satisfy the is associative. Therefore, you will write for this part. This is like this. Associative satisfying. Then for this part, you can write f plus f this vector addition g x f plus g x again vector addition h x. It is your f vector addition g again vector addition h x. So associative property satisfying. Okay, associative property satisfying. Thus addition is associative. Thus next for a inverse, what is the inverse for this part? Your inverse is let your function you take a set of x is 1 for all x belong to real number. Okay, it is your inverse function for this question. Okay, because you take addition of f vector addition to set of x, then you can get the value f again. Check this is your f is means again f of x. Okay, set this means 1, then you again get f of x. Similarly, set vector addition of f s is set means 1 into f of x, again f of x. Okay, so your additive identity is the constant function. Okay, for all constant function. Okay, right. Constant function that value is equal to 1. The constant value is 1. Okay, right. Thus, set of x equal 1. 1 is an additive identity. That means for this case, it's a constant function. That constant value is 0. That's 0. Sorry, constant value is 1. That function is an additive identity. Okay. Next, for the inverse. Okay. If you do the addition, right, for that for one of the element of that set, that inverse, get the inverse, then you get the value 1 because it's identity. Okay. So what is your inverse? Okay, what is your inverse? right? You define this function minus f x. Obviously, this exit because f of x is strictly greater than 0, therefore does not equal to 0, therefore this one exit. Okay, this one exit for all x belong to real number and this f of x strictly greater than 0, therefore this one exit. Suppose do the addition, right, vector addition to this one, then you get it is your f of x minus f of x, right? F of x is f of x minus f of x is 1 over f of x, then you get 1. It is your set of x, right? It is your set of x. Therefore, your additive identity is this one. Thus minus f of minus f, no? Minus f of x equal 1 over f of x is an additive inverse. It is your additive inverse. It is your additive identity 1. Okay, it is your additive inverse. Okay, next property axiom number 7. Here let C belong to real number. It is the scalar. So C scalar multiplication of f x of the form fx to the power c. Okay, fx to the power c. Fx is greater than 0, therefore fx to the power c also greater than 0. So c scalar multiplication of f, right? C scalar multiplication of f of x greater than 0. That means this c scalar multiplication of f belong to, right? C scalar multiplication of belong to which set B. So thus scalar multiplication closed. This is closed under scalar multiplication. It is closed. It is closed under, okay, it is closed under scalar multiplication. It is closed under scalar multiplication. Okay, scalar multiplication. Okay, next action number 7. Action number 7. Let f comma g in V and C belong to real. One of the scalar C belong to real. So C f plus g of x. So this is your f plus g to the power c. F plus g to the power c, that means you know c fx fx dx, no? Fx dx, again this is fx gh to the power c. So this is your fx c gx c. It's a power, no? Generally it's a power. Fx c into gfc. FFC, GFC, FFC means C scalar multiplication of F. Here is vector addition. It is C scalar multiplication of G. It is vector addition. Okay. Right. It is your for all C belong to real. Okay. Next property number 8. Take, okay, property number 8. Take 2 scalar and 1 vector. Let C comma D belong to real, right? C comma D belong to real and f in V. Okay, C comma D belong to V and f in V. So, right, C comma D f x. So this is, we will write fx to the power c plus d. F of c power d means f of to the power c into fx to the power d. Fx to the power c means fx to the power c means c scalar multiplication of f. It's vector addition. Okay, it is d scalar multiplication of f. Okay, therefore this property is also satisfied, right? If x there x, okay. Thus that is c plus d scalar multiplication of f equal c scalar multiplication of f d scalar multiplication of f. Okay, c is scalar multiplication of f, vector addition, d scalar multiplication of f. Okay, and property number 9. Property number 9. CD, let C comma D belong to real and F belong to V. Right. So CD F X. So this is your Fx to the power CD. It is your Fx to the power D into C. Is it okay? D, we will write, okay, no problem. Because CD, DC equal, because CD are real numbers, it's commutative. For a scalar multiplication, right? Right. This is your D is a scalar multiplication of F. Again C. Again C scalar multiplication of D scalar multiplication of F. X. So that is CD scalar multiplication of F, C scalar multiplication of D scalar multiplication of F. Action number 10. Action number 10. Right, action number 10. It is fx to the power 1, again f of x. Okay, thus that is one scalar multiplication of f equal again f. Thus V is a vector space because all 10 axioms are satisfying both this case. Therefore, thus V is a vector space. Okay, thus V is a vector space. Okay. Okay.